Last class we have discussed about what? Construction of a transformer and the working principle of the transformer. What is the working principle of the transformer? Faraday's laws of electromagnetic induction principle. Electromagnetic induction principle. What a transformer? What the type of device it is? What is it? What type of device? I have told you multiple times. What type of device it is? Electromagnetic device. Okay. With machines. Last in unit 2 we have discussed these machines. Okay. That it is electro as well as there is a mechanical part. So that device is said to be electromechanical device. In the second unit, third unit we will be studying about the transformer. Electrical energy is being given to the transformer to the magnetic core. Okay. So this is said to be what? The magnetic core. So it is said to be what device? It is an electromagnetic device. Or else we can say by means of some source only it is transferring some energy. Okay, by means of a source. So it is a, we can say that it has a passive electrical device. Okay, so we can say this as a passive electrical device. Okay, so since the sources are what? It is a passive energy. Okay, so it is can also be said as passive electrical device. What type of device is a transformer? Is a electromagnetic device. Okay, under what principle it works? The principle works on the electromagnetic induction principle. You all know that the electromagnetic induction principle whose comes to know the Lenz's law. Okay, so the induced EMF which will in the polarity minus. You have been studying that is E is equal to minus N d phi. What amount of flux being produced? That is minus N into d phi by dt. From that we are going to derive the EMF equations of the transformer. First, for what purpose we are going for an EMF equation of the transformer? It is used to find out the entire magnitude of the induced EMF. Now what source of voltage we are giving to this primary? Two sides are there. In center there is a magnetic core. Okay, so the left hand side what I have connected, it is a primary winding. Okay, so the primary winding we will be giving what energy? We will be giving a alternative voltage source. Okay, we will be giving what? AC alternative. Why can't we give DC source? I have told you last class. Why we are not giving the DC source as input to a transformer? Because in DC current there is no the principle of magnetic induction. There is no principle called electromagnetic induction in what current? Direct current. Okay. So we will be going for what? Alternating current. Okay. So in the primary winding I am giving what? Alternating current as a source voltage to the primary winding of the transformer. Okay, so since it is a transformer, it does what? It transfers. It just what is the function of the transformer? It transfers the energy, transfers the alternating energy from alternating voltage, or you can say that alternating voltage from one circuit to the another. It just transfers. Okay. In second unit in DC machines, what will we be studying? Converts. Okay, that is if it is a DC motor, it converts electrical energy to mechanical energy. If it is a DC generator, it converts mechanical energy to electrical energy. It converts. Okay, and here in transformer, as the name indicates, it's what? Transfers. It transfers the alternating voltage from one circuit to the another. Okay, so that one circuit is what? The primary winding to the another circuit, that is secondary. Okay, so the primary circuit is our input side where we are applying alternating voltage. Okay, we are not able to give the direct current over there. As I said before, there is no magnetic principle in the direct current. For that, we are applying what? Alternating voltage as an input to the transformer. I have told saying this multiple times. Just remember it. Okay. And next, now what does if I give an alternating voltage to the primary winding of the transformer? What principles will happen? Induction principle will happen. Okay, because it is a when I am giving a voltage V1 as an input to the primary winding of the transformer, who started the flow? The current I1 started the flow. So the current through this winding. Okay, in center who is there? The core, which is a conductor. What happens? An EMF is get induced. By that EMF, who is going to be produced? A flux phi is produced. The flux will flow through where? Through the core. This entire core will will have, you will carry a flux phi. Okay, so if the core carries the flux phi, the another side of the core which is connected to where, secondary winding, automatically the source of energy which I have given here transfers to where, given to the secondary winding, even though it is isolated here. Okay, three things of the construction transformer comes. One it is windings. Okay, next is this magnetic core. That one is what? Isolation. If it is a small size transformer, isolation are made by air, a simple air, or its vacuum or gas. If it is a large size transformer, the isolation is done by a mineral oils. Okay, that can be also serve as a role for cooling purpose also. Okay, so now here that is the three things in the construction of transformer. That is magnetic core, windings, as well as isolation. Okay, and now what happens when I am giving the voltage source V1, the current I1 flows through the primary winding. By that induction principle, who is produced there? Flux is produced there. The flux is then travels to comprises to where? To the secondary winding. So the secondary winding now having an alternative voltage. It just transfers, and based on the windings, based on the number of turns. Okay, so the primary winding number of turns is named as N1, and the secondary winding number of turns is named as N2. Okay, so based on the number of turns, either the voltage transfers, which is step up or step down, it will be predicted. Okay, if the windings of the transformer N1 is greater than N2, means it will be what? Step down transformer. N1 is greater, N2 is lesser. So this is a step down transformer. So if vice versa, if N1 is less than the N2, means it will be a step up transformer. The voltage level is get rise. If I am giving 11 voltage over here, means it will rises to some 33 over here. It is step up. If I am giving 33, means it will be, you can be reduced to 9 or 11 volt. That is what? Step down transformer. That we have seen in the rectifier cycle. What is that? From the back I have given 230 volt. I have used a small size transformer. What is it is converted, it transfers to what? The 230 volt is transfers to 9 volt. Have you seen? I have asked you to see the transformer. It is marked as 9 volt. Since center is 0, again at 9 volt. So the 230 volt is transfers to 9 volt. Okay. The level of the voltage is what? Then step down. Okay. For that purpose, we are going to apply a transformer. Okay. This is the basic. I have just given you a review. Now the flux is produced, right? The flux, it is the alternating current. If I assume that alternating current is sinusoidal, okay, what I am going to do? We are, for assumption, what we are taking, since it is alternating, the waveform is going to be how? Sinusoidal. So we are assuming the sinusoidal waveform as a input. Then the flux is producing here inside the core. The flux will be how means the flux is equal to the maximum amount of flux produced into the sine of in alternating current. What is there? In alternating current, even though the voltage transfers here, which will remains the same, I told you. Frequency remains the same. Don't forget that. Okay. Voltage level is getting level up or down, or even in ideal transformer the level may be same, but who is not going to change? Frequency is not going to change. For us, as I told you, for what are the standard frequency for India? It is 50 Hz. That is not going to change. Okay, there will be some approximation lesser one is about 48, 49. That is all technical, practical issues. But you don't need to worry about that. That is what standard frequency value is 50 Hz. That is not going to change. Okay, so that is what omega. With respect to, we will be doing with time t. Okay, what we are going to assume, the alternating voltage which we are giving as an input source, it is sinusoidal in nature. If it is sinusoidal in nature, what is the flux? The flux is equal to the maximum flux which is produced along with the sinusoidal nature, along with the frequency. Everything happens with respect to time. So it can be represented as phi is equal to phi m sin omega t. This is the equation number 1. Okay, next. For what purpose we are studying EMF equation? We have to find out the induced EMF. Okay, so now let us assume that the induced EMF is initially inducing, that is E1. Okay, E1 is equal to, based on what it is going to induce. If the induced EMF is inducing over here, it is N1 number of turns. Next, what will happen? It transfers to the secondary winding. again what happens? There will be some induction principle will happen here. So that is based on the n2 number of turn. First I am considering what the input side, the primary running side. The reduced EMF E1 is equal to minus n1 into d5 with respect to changing time dt. Okay, so that is shall we write out that is E1 is equal to minus n1 into d. Shall I substitute the first equation over here, which is phi is equal to what? Phi m into, since it is sinusoidal nature along with the frequency and the time, I can substitute phi as what? Phi m sin omega t divided by dt. Okay, shall we differentiate it now? This E1 is equal to minus n1. Let it be as constant. Okay, shall we differentiate the remaining thing? D by dt of sin omega t, what it is? Cos omega t. Okay, so omega into cos omega t. So that's a constant over there. So it will be become omega into cos omega t. Clear up to this? And now, what is our omega? Omega is the
2 pi.
frequency. 2 pi f. You know that is angular frequency omega is equal to 2 pi f. So, shall we substitute this over here? That it will become E1 is equal to minus
n1.
write it like this. 2 pi f into n1
Cos
omega t. Clear up to this? And next, we have the trigonometry formula, that is minus cos omega t. What it is? Minus cos omega t can be written as no sin omega t minus 90 degree, the reciprocal of it. If I take sin omega t minus 90 degree, it will be in minus cos omega t. So in place of minus cos omega t, what I am going to substitute? E1 is equal to, it is as it is 2 pi f into n1, then remains sin of omega t minus 90 degree. Clear up to this? So here I left one thing, right? Phi m. The phi m is also constant. Phi m into omega, and here also there is phi m. Here we have just differentiated what? The cos omega t alone, sin omega t alone. The sin omega t has become minus cos omega t. So, sin omega t become cos omega t. The rest of the thing, the phi m will be remains constant. That it is follows you. Okay. So, E1 is minus n1 d phi by dt. Next, what we have substituted? The value of phi which we have known. That is maximum value of phi m into sin omega t. I have just substituted in place of phi. That is as phi m sin omega t. Next, what I am doing? I am differentiating d by dt of sin omega t is what? Cos omega t. So that is minus, instead of minus n1 into this phi m will remain, since it is constant, the phi m will come outside. If I differentiate sin omega t, it will become omega cos omega t. Okay. The next what will happen? Omega is equal to, we know that it is 2 pi f. I have substituted the omega value in this minus 2 pi f into n1 phi m cos omega t. So we know the trigonometric formula, that is minus cos omega t can be written as sin of omega t minus 90 degree. So in place of minus cos omega t, I have written the remaining 2 pi f into n1 into phi m into, instead of minus cos omega t, written as sin omega t minus 90 degree. Okay, so take this as equation number 2. Okay, the next is, the next what we are going to do is we have to EM1. We have to assume that. Okay, EM1 is the maximum value of induced EMF. What we are going to assume? EMF as a maximum value of induced EMF. So that is, I am going to replace this 2 pi this thing. Okay, that is that E1 is equal to EM1 into sin of omega t minus 90 degree. Okay, so we have to replace what? 2 pi f into n1 into phi m, which is the constant there. Okay, the constant can replace what? That is the maximum value of E phi m. Whatever the angle will be, that is omega t minus 90 degree, whatever it may be, these things are going to be a constant. In place of primary value, who is going to be constant? 2 constant, pi is constant, frequency f is constant, n1 is based on the number of times which is built inside the design itself, n1 is constant, phi m is the flux based on the what alternating source we are going to, that is the maximum flux is to be constant. Okay, so only the sinusoidal nature is going to vary, so we can say that the constants over there 2 pi f into n1 into phi m can be replaced with what? It says maximum value of the induced EMF, that is we named it as E capital E M1. Okay, so now we can write the equation as E1 is equal to what? Capital E, maximum value of the induced EMF EM1 into sine of omega t minus 90 degree. Okay, take this as equation number 3. Okay, and similarly, if I do for the okay, next thing what I am going to do is I am going to find out the RMS value. Okay, that is as RMS value of the induced EMF, that is as in primary winding. RMS value of the induced EMF E1 in the primary winding. This RMS value is mentioned as E1. Okay, so RMS value we know that it's a root mean square. Okay, so that is what we have found the maximum value of induced EMF is EM1. EM1 is what? EM1 is what? EM1 is equal to the constant flow. Okay, that is 2 pi f into n1 into phi f. Clear? So, next what we are going to do? We have to find out the RMS value. RMS value is what? The maximum induced EMF divided by root 2. That is the RMS value of the induced EMF in the primary side. Clear? Similarly, for the if I do this, if I substitute this E1, E1 is equal to what is EM1? It is about 2 pi f into n1 into phi m divided by root 2. Okay, what is the value for 2 pi divided by root 2? If you do it, it will be 4.44. The value for 2 into what is the value for pi? 3.14. If we divide it by root 2, if I solve this alone, 2 into 3.14 divided by root 2, what I will get? 4.44. What are the remaining things? F into n1 into phi m. So the RMS value or the E1, the induced EMF overall in the primary winding is a value of what? 4.44 F into the primary winding. So N1 number of times into maximum flux phi m. Okay. Similarly for the secondary winding, how it will be? Only the number of times is going to change. So how the equation will be? E2 is equal to, here the equation is what? E2. Here the number of times is what? N2. So the ET will be E2 equal to say 4.44 into frequency is going to change. It's not going to change. Frequency will be the same. And next N2 is going to change. N2 will be changed. N2 into the flux is same over for the primary side. So the flux is also same maximum flux. That is phi m. Similarly for the E2. So in general we can say the EMF equation of the transformer as E is equal to 4.44 F into phi into N. Okay, so last class in the introduction part I told you EMF equation of the transformer. It is as 4.44 F into pi into N. Okay, so you write the winding. Similarly, we have calculated what for first part. That is from flux phi is equal to what? The maximum plus phi into sine of, since it is in sinusoidal, it's alternating what is the sinusoidal is the sine of omega t. Okay, we have direct induced EMF equation we have applied it. That is E1 is equal to minus n into d phi by dt. In place of phi, have substituted phi m sine omega t. After differentiating, I have got what? Minus n1 into phi m into omega into cos omega t. After that, what we have done? We have substituted omega is equal to 2 pi m. After what we have done? We have substitute a trigonometric formula. In place of minus cos omega t, we can substitute as sin of omega t minus 90 degree. So the equation will be like E1 is equal to 2 pi f into n1 into phi m into sin of omega t minus 90 degree. Later on we will be matching it with the maximum value of the induced EMF. That is as EM1. EM1. These constants 2 pi f into n1 phi m is replaced with the maximum value of the induced EMF EM1. Okay. Next what we have done? We have substituted the E1 over here. That is the small induced EMF E1 is equal to capital EM1 into sin of omega t minus 90 degree. Then what we done? We have just find out the RMS value of the induced EMF. RMS voltage we have taken it as capital E1. That is the overall induced EMF, or else we can say that EMF equations of the primary side transformer. Okay, primary side of transformer E1 is equal to maximum value of induced EMF divided by root 2, since it is root mean square. Okay, so after dividing it, we have found that 2 pi by root 2 is 4.44. So since it is primary winding, we have taken it as E1 is equal to 4.44 into F into N1 into 5. Similarly, for the secondary winding, how it will be? The induced EMF, or else we can say that the EMF equations of the secondary winding side. That is E2 is equal to 4.44 into the frequency remains the same F into maximum flux remains the same phi m into who is going to change? The number of turns will be changing N2. Okay, and next in general, how can we say that the EMF equations of the transformer? E is equal to, we need to mention E1 or E2. In general, EMF equation is E is equal to 4.44 into phi F into phi into L. Okay, so now take this as equation number. So here is equation number 5, and this is as equation number 4 here, and this is equation number 6. Okay, so now in the sixth equation, what I am going to do? Frequency is what? Same. Okay. So for per unit of frequency, how the value will be? Okay. So for per unit means the EMF induced is what? E. Induced EMF per frequency. Induced EMF per frequency means if I divide F over here means what it will become? Cancel. F and F will get cancelled. So what will the term remaining? 4.44 into n into 5. Clear? So we can say that the EMF equation or EMF induced in a transformer per frequency for one unit frequency. For per frequency is the constant of 4.44 into number of times n into 5. Okay, these are all you have to write as a description. EMF equation per frequency is 4.44 n into 5. Okay, and next, this is by that is EMF equation per frequency. Now, what I am going to consider is I am going to consider the fourth and the fifth equation. What are the alternate things we can able to find out by using the EMF equation we are seeing? Okay, that is by finding out the EMF equation, I can able to find out EMF induced per frequency. Next, I am going to compare the fourth and the fifth equation. What is the fourth equation? E1
4 equals to
equals to what?
4.
E2. If I compare these two equations, okay, how it will be? E1 is what? 4.44 F into N1 into phi m. Here what will be? 4.44 F into N2 will be phi m. Okay, so now what I am going to do is represent, or we can say that, see listen, we can say that I am comparing the fourth and the fifth equation, E1 by E2. Okay, I am comparing the fourth and the fifth equation, we are going to say that E1 by E2 is equal to, what is the value for E1?
4.44.
Instead of cancelling like this, we can cancel like this. Okay, 5 m divided by 4.44
F
n2 5 m. So we can cancel 5 m over here. 4.44 cancel. F and F will get cancelled. What will we get when we comparing the EMF induced in the primary winding and the secondary winding? We will be getting as E1 by E2 is equal to N1 by N2. Okay, and now I am rearranging it and writing. That is E1 by
N1
N1 is equal to E2 by N2. What conclusion we are going to give is the EMF induced in the primary per turn. Okay, the EMF induced in the primary per turns is equal to what? The EMF induced in the secondary per turns. Can you now just imagine the EMF, the primary set and EMF is induced. The number of turns is 3. Okay, so the value divided by 3. The voltage we will be getting a particular voltage value there. Okay. The same is getting transferred to where? Secondary winding. There the number of times may be more than the primary winding. For example, you can take it as 5. Okay, so now what is happening? We get the EMF E2 divided by, we will be substituting the number of turns as N2. So this is how the relationship between the EMF induced in the primary winding per turn, which is equal to the EMF induced in the secondary winding per turns. Okay, so this is all primary winding number of turns. This is the secondary winding's number of turns. Okay, have you understood this conclusion? What we are giving? EMF induced in the primary winding per turn. Per turns means the turns of the primary winding model is equal to what? EMF induced in the secondary winding per turns, which is in the secondary winding. Okay, so that is how we will be getting the final of EMF equations of the transformer. Have you all thorough with this EMF equations of the transformer? Basic from the initiating line to till the E1 by N1 is equal to E2 by N2 you have to write it. Okay.